Okay, let's go to page 152 at the top. And the very first formula that we're going to get you to be familiar with is something called the distance formula. And this is a formula which we are going to use if ever we are asked to find the length of a line. Right, and the best way to get us into this is to just throw us into the example. And it says, have a look at the diagram below. Take out your ruler and measure the distance from A to B. All right, now I'm not going to be able to do that, but literally, can you see that if you were to actually have a look at any distance along this horizontal x-axis, if I asked you to work out the distance, let's say, from this point, and I don't want to call it A, let's call it point P to point Q, we would be able to say that that is 1 unit, 2 units long. All right? If we were going from P to R, we would say that that was 1 unit long. Even if we were going from this point here to Q across there, can you see we would be able to count off 1, 2, 3 units in length. The problem comes when what we are trying to do is to measure or know the length or distance of a skew or an oblique line. So we have got a skew, and a fancy name for that is an oblique line. All right, so we've instructed you to pick up your ruler and to measure it, and I'm hoping that when you measured it, you actually got it to be 5 units in length. Okay. But that's going to be quite tedious. If every time we give you a skew line, you have to actually draw up an axis, set it up according to scale, everything has to be absolutely accurate, and then you've got to take out your ruler and you've got to measure the line. Okay, that's going to really be heck of a painful if we try to ask you to do that every time. Okay, so what I want you to focus on, guys, is I want you to focus on this point A, down to C, and across to B. Now, can you see that what I've done there is I have actually traced out a triangle with the name ABC, all right? Now, looking at that triangle just a little bit closer, can you see that this is a vertical line, this is a horizontal line, and they meet at 90 degrees. So I'm going to say that in this triangle, angle C is a 90-degree angle, and I'm sure you can see that. Right, so going back to grade 8 and 9, we have a theorem which we can apply every single time we have a right-angled triangle. And that we can accredit to the chap by the name of Pythagoras, and his theorem actually says to us that when we have a right-angled triangle, if we label the horizontal x and we label the vertical y and the hypotenuse r, it tells us that x squared and y squared actually is equal to r squared. So that's exactly the situation that we have here. So if only I could work out the length of the horizontal and the length of the vertical and pop them in here, then I would be able to get the length of this oblique line. So in this particular question, let's have a look at what our horizontal would be. Now, do we agree that this x value is -1? This x value is 3. So moving across from -1 to 3 would be moving across to the right by 4 units. So my x value would be 4 squared. And my y value, all right, we want to have a look at how long the y line is. So the y value up here is 2. The y value down here is -1. So in fact, if I went from -1 up to 2, I would be moving up 3 units. Or if I went from 2 down to -1, I would be moving down 3 units. But whether I move up or down, it's still 3 units long. So my y value is going to actually be 3. And so substituting that in, I'm getting 4 squared and 3 squared is equivalent to r squared. So 16 and 9 is my r squared. So r squared, of course, comes to 25. And so if we square root both sides, r works out to be 5. So that is the algebra behind how we would find this distance of this line. Okay, relating it back to grade 9. But we really don't have to go through that every single time either, because for that we need to have the picture. So what we actually furnish you with is a formula which allows you to do this. And we call it the distance formula. And the distance formula tells you that if you are wanting to find the distance or the length of a line, we need to work out the difference between the two x values and square it, and then the difference between the two y values and square it. And that's actually exactly what we're doing there. When we put in 4, it was the difference or the length of the x piece, the difference or the length of the y piece. And why is it square rooted? Because that's the actual distance. Can you see that here it's the distance squared? So guys, let's have a look at our picture. We know that our a value is -1, 2. We know that our b value, as they gave it, is 3 minus 1. So let's imagine that in the question it just said, find the length of AB. We don't even have to draw it. So we would immediately go to our book and say, right, the length of AB is, and we're going to pop it into the formula and just be very careful that we put it in correctly. So the x value at A is -1. Subtract the x value at B is 3, and we're going to square that. Then we're going to put an addition sign, and we're going to say the y value at A, which is 2, minus the y value at B. Now notice that the y value is negative, so as I actually introduce it, I've got 2, subtract, then the y value at B is a -1, close that off, squared. And so my answer for that is just going to take a little bit of working out. So -1 minus 3 gives me -4. -4 squared, all right, is 16. And 2 subtract -1. Okay, 2 subtract -1, of course, is actually the same as 2 plus 1, because the minus times the minus gives me a plus. And then I'm going to square that. So I'm getting 2 and 1 is 3 squared, which is 9. And of course, we land up with the square root of 25. And our answer, as we got when we saw it previously, is going to be 5 units in length. Okay, now, really, that's not difficult. How do we actually get you to demonstrate that you know how to use the distance formula? Use the distance formula to show that triangle ABC is an isosceles triangle. So for me, what's important here is they're actually giving me the method. They are also telling me that I need to show that something is an isosceles triangle. All right, so let's just quickly go through the detail that we need. And of course, if we're going to show that something is isosceles, we need to actually know what isosceles means. Okay. Right, so we basically get triangles categorized according to either their angles or the length of their sides. Okay? Now, an isosceles triangle is categorized according to the length of its sides. If we have a triangle, any triangle, with all 3 lengths different, then this is actually called a scalene triangle. Okay, so if all 3 lengths are different, then it's going to be a scalene triangle. Right, now what happens if we actually force not all three to be different, but two of them to be the same. So if two are equal in length, then this is the chap that we need. This is called an isosceles, and I've spelt it incorrectly, isosceles triangle. All right? Now, if we refine our triangle even further, so here they're all different, here we force two to be the same, and here we get three to be the same, so three are equal in length. Then what we call this is an equilateral triangle. Okay, so basically what they are going to be asking us is if they ask us to prove that it's scalene, we're going to have to prove that all three lengths are different. If they ask us to prove isosceles, we're going to have to get two to be equivalent or the same. And if they ask us for equilateral, then we're going to have to work out all three lengths and get them to be the same as each other. Okay? So let's go back to our picture and have a look at it. Now our triangle has been placed on our XY axis. They give us the coordinates of A, B, and C. Now we cannot just take out our ruler and measure because this thing hasn't got a scale on it. It hasn't been drawn accurately at all. Okay, so what we need to do is we need to use our distance formula on AB, our distance formula on BC, and likewise our distance formula on AC. And once we've done that, we can actually then validate whether it's isosceles, scalene, or equilateral. So what we're going to do now is we're just going to repeat the distance formula for each of the lengths. Right, so let's start off. It's not difficult, it's just going to be repetitive and you must be accurate. So for the length of AB, all right, we are definitely going to need the coordinates of A, which are going to be -2, 0, and the coordinates of B, which are going to be 2 and 3. Okay, we don't need the picture at all, we're just going to plug it into the formula. So I write D for distance, and then a subscript AB to mean the distance of AB. And now I'm going to plug it into my formula. So remember it says x at A, which is going to be -2, subtract x at B, which is going to be 2 squared, and then the formula says y at A, which is 0, subtract y at B, which is 3, and we're going to square that. Now, that is not difficult, as I said before. You just have to be particular that you put it into the formula and you don't mess up in your arithmetic here. So, -2 subtract 2 is -4. If we square that, we get 16. And 0 subtract 3 is -3, and if we square that, we get 9. So it does look like the distance of my AB is again our familiar square root of 25, which is 5. All right? So now we've done AB. We now need to go and work out the distance of the other line segment, and let's work with the distance of BC. Now remember, we just need to have B, and the coordinates of B are 2, 3, and we also need C, and the coordinates of C were 1, -4 as given to us. Right. Now, remember our formula as I taught it to you was the x at A minus the x at B. But that is just A's and B's are a generalization. They can be any letters at all. So I'm going to take the x at the 1 point, which is a 2, subtract the x at the other point, which is a 1, and square it. And then I'm going to take the y at the 1 point, which is 3, and subtract the y at the other point, which is a -4, and then I'm going to square that. Right, so reckoning that, we're going to get 2 subtract 1, which is 1 squared, which is 1. And, now just be cautious, we've got 3 subtract negative 4. Of course, that is 7. 7 squared is 49. And, of course, that is going to land up being the square root of 50. Now, the square root of 50, if we were to simplify that, is the square root of 25 times the square root of 2. And so another way to write this would be 5 root 2, because we could square root out the 5 and then times it by root 2. Okay, so our next step is to find that third and final side. So from our picture, we now know that we also need to find the distance of AC. So, of course, for me, I think it's important that I just write down the points, A as being negative 2 and 0, and B, C as being 1 and negative 4. And now we are going to find the distance of AC. All right, now remember the distance formula says exit A minus exit B, but who cares whether B is now replaced with a C? It's just exit the first minus exit the second. So it's going to be negative 2, subtract 1, square it, and 0 subtract negative 4. And I know that you're going to be happy because I've explained it twice already. The subtract the negative is going to give me that as being a plus 4 squared. Right, just doing the arithmetic, negative 3 squared is 9, and 4 squared is 16, and we're familiar with this chap from previously. That's the square root of 25, and we know that that is 5. Now, unfortunately, if you finished your workings out there, you would not get full marks, because all that you've really done is you've worked out the length of 3 sides. You haven't tied it together and shown what they asked. Remember, we had to show that it was isosceles. So I would now finish off my sum and I would say, right, so AB is 5 units. The one that we did next was BC, and we got BC to be 5 root 2, or if you left it as an unsimplified surd, the root of 50. And lastly, we've got AC to be 5 units. And so now I can actually say, well, look at that and look at that. Those are now equal. So how am I going to prove it? I'm still not done. I now need to say, therefore, AB is equal to AC, which makes it an isosceles triangle. Okay, now the one thing that we also like to ask, and it's not here in this particular example, is perhaps your teacher might add on an extra question and ask you to work out the perimeter of triangle ABC. So notice that having done all the legwork to work out the perimeter of ABC, you are just going to have to take the one length, the second length, and the third length, and then you are going to have to add them. So if we've got our triangle ABC, we know that it's going to actually be AB added to BC added to AC. Right, and we worked out AB to be 5, and we worked out BC to be 5 root 2, and then we got AC to be 5. And you can see that these two are like terms, so I'm quite happy to say 5 and 5 is 10, and 5 root 2. And it depends on the question. If they said leave it in simpler surd form, then I'm done. So this is surd form. All right? But however, if they said take it to 2 decimal places, you would then have to go to your calculator and feed that in and give it back to us in 2 decimal places. And that, guys, is the distance formula. They can't ask you anything else other than to work out the length of a line. Maybe work out the length of the sides of a quadrilateral or a triangle, but that's it.